You out there in internet land have no idea how many times I've tried to do this video. My computer is completely crapping out. So I'm on Brian's computer now, ordered another computer. Just want to get through this design example. So let's try. Okay, the last video, which seems like a long time ago, we came up with the minimum amount of bonded reinforcement, which is what we did to start with the beam design, and one-way slabs, same thing. In fact, you'll notice a trend here. A good post-tension design is governed typically by minimum bonded reinforcement. The flexural strength check is really just kind of a check. It's now sometimes we need to add a little bit more for strength, but that's more the exception rather than the rule. And I think you're actually going to see that here. So that's telling you have a good design. It tells you have the right slab thickness for the loading that you have. You've made good decisions if this is the case. If you, on the other hand, are coming up with needing a lot of flexural reinforcement at a lot of locations, and you're well past minimums, probably a good idea to reevaluate the slab, or the one-way slab, the two-way slab, or the beam depth that you have been working with. Okay, so this is interesting and frustrating, and I'll tell you all those parts. So we're looking at the 30-foot slab span, and that has a span to depth ratio of 45, which is greater than 35, and according to the code, we use this, which is originally, well, always intended for the slabs, for the slab design. What I will tell you, though, is if you go back to this design, we're looking right now at the negative moments here. And I've just done the span to depth ratio on the longer side. But had I done it on the shorter side, you'd actually find that it's the beam equation, the other equation that will control that side. And that's really ridiculous. That is a silly thing about the way the code is written. The code decided, instead of just saying for slabs up to a certain thickness, which would have made a ton of sense, they had to be cuter than that and come up with span to depth ratios to describe which FPS equation to use. Well, it's not uncommon in two-way slabs to have the short spans controlled by the beam, what I call the beam equation. And what's really strange is when that'll show up is when you're doing a design and you're using one of the real cool hip finite element programs that actually does the rebar for you and even draws it, and you look at the plans and you see reinforcement when you're looking at the flexurally required strength reinforcement, and you see it on one side from the center line of the column towards the longer span, but you see no bonded rebar in the other direction. So you have bonded reinforcement that's stopping right at the midpoint of the column. And that's actually what the program is doing, is it switched FPS equations. So on the short side, this goes to 1, you get to go up to 60,000, and you'll have 30 KSI more usable stress at ultimate on the shorter side because you switched equations. Then you won't need the bonded reinforcement. But on the longer side, you end up needing the bonded reinforcement for strength, maybe. So anyway, we've seen strange situations like that. I love to ask the designer, what's happening here? Why are you only showing bonded reinforcement requirement in your calculations from the midpoint of the column to one side of it and not the other side? And so far, nobody has ever had an answer for me. I know the answer, and now you know the answer. But anyway, we'll keep that our secret. Okay, so easy equation to use. I'm going to pick up the speed a little bit because I'm trying to cover a lot of stuff. And by the way, I've done this video numerous times now. You just don't know that. And then something goes wrong and I have to start over. So BD, let's remember what B is. B is the entire width of this design strip, 29 foot 6. We're designing the whole thing. So that's what B is. D is just this little, 8-inch slab minus cover, to the centroid, 6.75. So, okay, big B, little d. FSE, same as it was in beams, same as it was in one-way slabs, and same as it is in two-way slabs. It's the same idea. We're stressed to 0.7 FPU or anchor at 0.7 FPU, stress to 0.8 FPU, and take a long-term loss of 15 KSI. So in this example, to the longer side, we have a 198.5 KSI. And in my example, I don't show you that the other side is about 30 KSI more than that. But you know now. Okay, limited to, this is never going to govern. It didn't govern before, and now that we're at FSC plus 30 KSI, not 60, it's really not going to govern. So the maximum in two-way slabs, what's intended, is to be 204 KSI, not 234 like we were in beams. But we calculated less, so we'll use the less, the 198.5. Now everything at this point is the same, and I'm not going to spend a lot of time going through this because this is just exactly what you've been doing. The post-tensioning and the bonded steel are at the same elevation. They have the same cover. Pre-stressing uses the FPS equation times 18 strand. I told you it was going to be easier if I used a round number. 0.153 square inches, and we come up with a force of post-tensioning. We had minimum 5 number 6 bars for bonded reinforcement, so multiply that by 60 KSI. The sum of those must equal this. Statics also applies, by the way, to two-way slabs. We calculate a CC and an A depth, a neutral axis depth, which you'll see we really don't need. And we calculate a strain way greater than 0.005. So slabs, you're going to find out, you'll do that calculation once, you can find out that they're always tension controlled. We don't ever really, I should never say never, but you have a weird situation, by the way, if you start getting compression steel requirements in your slab. But in this case, we're nowhere near needing compression steel. We have a tension controlled slab, and we sum moments, same thing you've always done, and find out that we have substantially more strength than we needed. Remember, the demand moment, the controlling demand moment was on the inside, the longer span side of the interior joint. And just minimum rebar with the post-tensioning that we have easily satisfies that. Okay, let's move over to a span. Let's go to the span 2, the longer span, the 30-foot span. This is a completely different minimum area of steel. Now, remember, we have already checked to make sure that we were less than 6 square root F prime C. Two-way slabs limited top and bottom to 6 square root F prime C. That's the average stress. But we also had to keep track of where we exceeded 2 square root F prime C at the bottom of the slab. Because that's, that's where the code and very smart people like my dad, I think, and others decided that it would be a good idea to add bonded reinforcement. And they're saying at 2 square root F prime C. Now stop and think about that for a second. We run along and we analyze and we say that concrete cracks at 7.5 square root F prime C. And because we're using an average stress of, knowing that we have higher localized stresses near the column, but we limit our two-way slabs to 6 square root F prime C. What are we doing adding rebar at 2 square root F prime C? Well, like I said, years of practice, people have decided that that's a realistic point to start worrying about cracking the concrete. In reality, the fact that you're going to have temperature and shrinkage happening before you ever pre-stress this thing while it's sitting in the forms, you have restraint. You have restraint of the seismic system, the walls, even the non-seismic walls may be restraining your system. Columns, stiff columns will restrain the system. So in reality, never ever market a crack-free slab. You know, you're going to be a lot less cracking than a rebar slab, but never say it's not going to crack. And, you know, like I said, what some pretty smart people decided at 2 squared F prime C, let's put in bonded reinforcement in the bottom. And it's a good idea. Now, one of the worst design decisions I ever see are people limiting their bottom stress to less than 2 squared F prime C. They actually set that in the program and force not needing bonded reinforcement. I can't emphasize enough that bonded reinforcement is your best friend. The best designs in post-tensioning have the least amount of post-tensioning. So if you are limiting your bottom stress to 2 squared F prime C, you're probably putting in more post-tensioning than you would otherwise. And now you're exacerbating the problem. The restraint's going to be worse. The cracks you do have are going to be thicker. They're going to be wider. And now you've forced a situation where you don't have any bonded reinforcement crossing those cracks. It is a terrible design decision to try to limit your stress to less than 2 squared F prime C in the positive moment regions. Please don't do that. Let it get up to 6 if it needs to. Put in the bonded reinforcement. In fact, we won't do a two-way slab design that doesn't have a mat of bottom steel in both directions. We will never be less than 4s at 30 in both directions. Need it or not, that's what we put in. Because we understand that there's a whole bunch of things that can happen that are beyond your control. The contractors make decisions that you can't control that may result in the slab cracking. So you want that bonded reinforcement in there. So, okay, made my point. What the code says is when you do exceed 2 squared F prime C, you are going to put in an area of steel. It's calculated by some NC factor divided by 0.5 Fy. NC is the resultant tensile force acting on the concrete. What that means, and I think I told you before, it was fine. We calculated the maximum tensile stress at the bottom of the slab. We were way less than 6 squared F prime C. We were happy about that. But we were in excess of 2 squared F prime C. It was important, I said at that time, to also calculate the stress on the compressive side, on the top of the slab. Because you need to establish this line and you need to establish that depth of triangle. So this is how NC is calculated, and you need to know the top stress and the bottom stress when you have exceeded 2 squared F prime C on the bottom. So N sub C is really just this area of stress multiplied by the tributary width, that 29'6". So that's what we're going to calculate. It's a relatively simple calculation. I would say a lot of people don't understand how to do it though, but once you do, it's pretty simple. This area is 1/2 0.164 times 1.97. The total force is acting over the entire width of the tributary area, the width of the slab beam, the 29'6". So we come up with a total force, this N sub C force, of 57.2 kips. That's what we need to provide rebar to resist. And the rebar we provide, it's not yielding, it's considered to be half of yielding. So we're only putting it in, making it work at 30 KSI. It doesn't make sense to put in crack control steel and expect it to yield. I mean, that's something strange about that. This is just arresting cracks. So the code says we'll assume it's at 30 KSI, not 60 KSI. So we come up with needing in the long span in the bottom 1.9 inches square inches of rebar. 10 number 4 bars provides 2 square inches of rebar. Let's do that. In this case, that results in a spacing of 35.4 inches. So number 4 is at, we'd use number 4 is at 30, and that would satisfy that. We would, you know, the computer program, PT data would do this calculation, but we've told it that we have 4 is at 30, so it wouldn't add any more to that. So the length of the steel that you need to provide of this minimum steel, remember we're not talking about what's required for strength. We haven't checked that yet. This is the minimum steel, and what we're going to do first is establish minimum steel and its length, and then we're going to go check that for strength. ln over 3 centered in those areas. So ln being that distance right there, divided by 3, about 10 feet. We're going to add a, PT data is going to add a bar cutoff to each side and then round to, I think the closest 6 inches. So we end up with, it's telling you you need 10 number 4 bars by 11 feet. So we verified that 35.4 and that 10.4, or 10 number 4, sorry. So that's it. Now, like I said, this is what's required by code. What you're looking at is required by code. What Seneca Structural Engineering is going to do is just provide 4s at 30 throughout the whole thing in both directions. A nice grid of bonded reinforcement at the bottom, and don't let people tell you that you've just blown the cost of the entire project. Not true. We still get tons of our projects. It's still less rebar than anything else is going to be. Certainly less than a rebar two-way slab is going to be. Okay, so we've come up again with the minimums. Now we're going to check the moment capacity, the strength requirement. So in the 30-foot span, we're really doing the same calculations we did before. That's still the same span to depth ratio that we had before. So that's the same FPS equation. Shockingly, we're going to end up coming up with, without me walking you through the whole thing, the same exact 198.5 that we did at the top. DP was the same in both directions. Section modulus is the same top and bottom. Two-way slabs got easier that way. So I go to show you that the same 204 maximum was the worst we could use, but we're using less because we calculated less. Set up the same force diagram. Instead of I think 5 number 6s that we had on the negative side, we have 10 number 4s on the bottom side. Calculate TP, pre-stressing, bonded reinforcement. Those two must equal compression in the concrete. We calculate a Whitney stress block depth, neutral axis depth. Again, that strain is basically the same as it was when we were looking at the negative moments. Much, much larger than it's required to be tension controlled. So we use a phi of 0.9, and again calculate, just like we always do, some moments, and come up with much more strength than our positive demand moment was. If you go back and look, our positive demand moment in the middle of span 2 was 275.4 foot kips. Minimums is going to provide that. Okay, so we've looked at the slab for flexural strength. We provided minimums first, top, checked the top steel flexural strength capacity using the FPS equation. We did the same on the bottom. We found the different minimum requirements on the bottom, calculated the strength associated with that, and in both cases we were substantially greater than the demand moment in those slabs. Not unusual. In fact, this slab is highly usual. It's typical. These spans of 30 feet are very typical in a two-way flat plate slab. 40 pounds a square foot, that is your parking loading. We threw in 3, for fun, but your apartment loading is 40 pounds a square foot. Condominiums, You're not going to be typically much higher than that. So this design is normal. You'll see this same thing happening in your designs. Okay, punching shear. This is where things get interesting. The truth of the matter is post-tension slabs don't fail in flexure. It's almost impossible. Even when they go and they're loaded way past the Whitney stress block depth, some moments, and come up with an FPS capacity, then they test those slabs and they grossly exceed the capacity that you calculate. They always do in testing. There's a membrane action, there's a catenary action, there's all kinds of ways to try to explain why they have so much more strength than our numbers actually say. But what doesn't is punching shear. Punching shear is the thing we really want to focus on, because remember, compared to rebar slabs, we have thinned the slab. This slab would be 10 inches or 11 inches in a rebar deck. It's 8 inches in a post-tension deck. So we have, we've done great things, but we've hurt ourselves in the punching shear category. So we have to really take punching shear seriously in post-tensioning. So I've gone back to chapter 6 of my own book to refresh you on how this works. Now we're looking at an interior column. We're bending about this axis. So we're bending this way. These are, because we're in 3 dimensions now, these are the faces that are creating the stress. Remember, in a beam, we look 2-dimensionally at the moment of inertia. And we had a moment of inertia of BH cubed over 12, and a section modulus of BH squared over 6, and we were calculating the stress at the extreme faces due to bending. What we're doing here is the same thing, but 3-dimensionally. So we're bending about this axis and creating stresses on these faces. And that's what this looks like. There we break this up into a direct stress, just a VU or PU if you like that better, from the slab, the shear of the slab. I don't use PU because that indicates like a column moment coming from the top, but this is from the slab at that level divided by this area. So you have your direct shear stresses, and then you have your bending shear stresses. And the bending happening about here creates a stress on this face, it creates a stress on this face, and it creates a triangular type distribution on these faces. Now, I am operating under the assumption that you've had this at some point in your career. Hopefully in a rebar slab, not in a post-tension slab. So, and this is the same either way. Now, if you never did get exposed to this in a mild reinforced slab, then you probably want to go through my chapter 6 a little more closely, and then your own reinforced concrete book a little more closely, and get refreshed on what punching shear is. But this is the idea. This is the refresher course. In edge columns, it's the same thing, but we have a different area. We only have 3 faces working for us if this is a free edge. So this is what our bending stresses look like, and this is what our direct stresses look like. And I had fun deriving all these things, and yes, I did do it just for fun. It's my book. I don't want to steal from anybody else, and it took me back to my analysis, mechanics of materials, stuff like that days. Now, I'm glad I'm not doing that anymore. So, anyway, you can go through and look at what corner columns do and see what you have to do there. They're not symmetric anymore, so you have a little bit of a strange stress distribution, but that's the point. Okay, so now back to our example. We are bending about this axis And this is our direction of analysis. So calculate the area of concrete that's experiencing those stresses. That's running around here. We calculate that torsional moment of inertia. Stresses that are being created that look like those triangular things, and then stress down here and stress up there. Now here's where it gets interesting, and if you have not had this before in reinforced concrete and rebar concrete, pay attention here. What the code says is you calculate your shear stress, the punching shear stress, and compare it against the allowable, but you're not using the total unbalanced moment. Remember, we've done that moment distribution. We have a column, so we have a different moment on the left side than the right side. That difference is the moment that has to get into the column, and that is the moment that's creating a shear stress. It's the resistance of the column that's creating problems for us in the slab. There's additional stresses happening because that column's resisting the bending that the slab wants to do. So there is an unbalanced moment. We get that from the moment distribution. What the code says is you're only required in these punching shear analyses to account for a portion, a percentage of that unbalanced moment in the shear stress. In the remainder is taken by flexure in a flexural stress. So the rebar that we calculated over the top of the column is responsible for the gamma F times the unbalanced moment. The shear stress calculations for punching shear stress that we're doing only have the gamma V portion of that unbalanced moment. So like I said, I hope that's a refresher for you. If it's not, study that a little bit more, because that's an important concept. Now, how someone really came along, or people came along and said, okay, we have this unbalanced moment in the slab, that's got to get transferred to the column, and we're going to use two different mechanisms to do it. We're going to use the shear stress in the slab, and we're going to use the flexural capacity of the slab. And between the two of those, it needs to get the total unbalanced moment into the column. Okay, I guess that makes sense. I'm sure there was plenty of testing that backed that up, but what that testing said was this is how you calculate the percentage of the unbalanced moment that has to be transferred in shear stress by shear. Okay. Now back in chapter 6, I went over what C1 and C2. C1 is the direction in the analysis. C2 is the perpendicular direction. And that's goes into this equation. Typically, on an interior column, it's in the range of 40% of the unbalanced moment in our moment distribution at the columns that has to be taken by the shear stress. Okay, here's another point. So take a sip of coffee, deep breath. So the unbalanced moment, how do we calculate that? There is a demand moment on the exterior side of the column. So, So we did a moment distribution. We had a moment on this side of the center line, and we had a moment on this side of the center line. We calculate, and this is this is where my dad stepped in and decided what to do. Now the code, in my opinion, is very unclear on this. And I'll show you what my dad did in PT data and why I think he's absolutely right and why he did it. We are going to include the secondary moments and shears in this calculation. And I know I've said all course all along that secondary shears are relatively small, and it was a code decision not to put them in there. The code is very ambiguous, in my opinion, on how to calculate punching shear stresses. But what Dad decided, and I think Dad is right, He came up with a demand moment on one side that includes the secondary shears. I'm sorry, includes the secondary effects, secondary moments. The demand moment on the other side, which includes the secondary moment. And those two are going to be the two moments that generate the shear stress. So I know I've made that sound confusing. Remember, we're checking punching shear. We're doing a shear analysis. We're going to get to that shear by looking at the unbalanced moment that we have. So those moments are going to include the secondary moments. So effectively, you're including secondary effects in a punching shear stress check. I hope that's okay with you. I'm going to show you why. So if we go back, we had a dead load moment demand, a live load moment demand, multiplied those to get demand moments or ultimate moments, 1.2 and 1.6. Then we had a secondary moment. It was very small on the shorter span, on the 15-foot span side. So it doesn't make much difference. And you know, we could make the decision that, well, we could ignore that one. We're not. But PT data doesn't. And if you want to be matching the numbers like I like to, you're going to have to include it. Now look at the interior side. Remember, these are the moments. So the moment, the secondary moment, is not insignificant. It's something that needs to be in there. And that difference between these moments is going to end up generating the unbalanced moment, by which we calculate the amount we have to transfer in shear. So I know I've said shear, secondary effects, secondary shears are relatively, I don't want to say unimportant, but the code doesn't make you include those in most shear analyses. But we are including secondary effects this way. They're coming through the moment side. Okay. So the unbalanced moment that we're talking about, and you can make the argument that the code does say, you know, include secondary effects in moment analysis, but this isn't really the moment design for the slab that we're doing. We're going towards the punching shear, but that was a decision that Dad made, and I think it's the right one. So sorry if I've confused the heck out of you. But to calculate the unbalanced moments, we're going to have secondary effects in there. Bottom line. That's what PT data does. So we're looking at the direct load, the PU value, just the shear direct force, and live loads. And we come up with 79.59 kips, dead load, 30.9 live load, and come up with just a PU factor. That's going in the direct shear calculation. Remember, we have two shear components. The direct shear, the VU, divided by the area, the three-dimensional area of that critical section. And then we're adding the shear stress due to unbalanced moment. So the unbalanced moment was 40.09, which was calculated using secondary effects. It goes here. The percentage of that we're required to include in a shear stress calculation was 42.2%. Multiply that by 12 to get it to inch kips, and then we're multiplying by the distance between the centroid of the section to the far face of the critical section. So just like we would a YT or a YB in a beam. And we're dividing by the polar moment of inertia. So look at these equations. Just take a second and look at them. There's only one difference. On the interior side, these are additive. On the exterior side of this, the unbalanced moment is actually subtracting from the direct shear stresses. So that's not the critical side. And that's what the calculations are going to show. This is the one we're focused on. And that makes sense. That's the interior side. That's the 30-foot span side. That's the side that should have the highest shear stresses. Okay. What's the allowable punching shear stress? Interior columns has a different allowable punching shear stress than exterior columns. And I go through that a lot in Chapter 6 when I'm going through this. So if you're interested in that and you want to do any of your own calculations on edge columns or corner columns, go read that. The code decides to be confusing on that. It's fairly straightforward in the equations for the interior calculation. So we have two equations we have to check, and it's the lesser of the two of these. So 3.5 square root f prime c, that kind of looks familiar, doesn't it? Plus a 0.3 FPC plus a vertical shear portion, vertical component of the pre-stressing. Vertical component of the pre-stressing. Now, just like we did before, we're going to ignore these because we don't feel confident enough that we know exactly what right at the edge of the critical shear plane, what that vertical component of all of our pre-stressing is. It's kind of a scary thing to include to help yourself when you don't know it that well. So I think PT data, I'm where all software just ignores that part of it. We suggested taking it out of the code since nobody ever does it and uses it, but that got fought vehemently by people who've never used it themselves. But they still want it there, just in that weird case that something goes wrong and they might have to use it. So, okay. This is a more traditional, if you're used to calculating punching shear in rebar slabs, this looks more like what you're used to seeing. But then they gave you a benefit for being pre-stressed, which makes sense. I mean, that stuff actually makes sense to me. These equations do make sense to me. You know, unlike some of the other equations we've talked about for beams, the VCI and the VCW. This will go to 0. Strange thing in the code. The code says that the square root of f prime c cannot be taken greater than 70. Which means that no matter what your slab stress is, you're not allowed to assume that or your slab compressive stress, you're not allowed to assume that it's any more than 4,900 PSI. So if you have a 6,000 PSI slab, you're still doing a punching shear stress at 4,900 PSI, or your computer program is. You may not know it. The code. So that's what happens when you use data and research that was done 40 years ago when 5,000 PSI slabs was a lot. Things are different these days, but the code doesn't change. So if you've done rebar slabs, gamma S is the same. It's taken as 40 for interior columns. We've already calculated that the direct compression in the slab is 169 PSI. Now, the code says, we're taking the average pre-compression. This is a two-dimensional, we're getting pre-stressing from 2 dimensions. We're checking punching shear on a 3-dimensional system. Our analysis is only in one direction, and in our one direction, we've got 169 PSI compression. PT data is not sure what you're designing in the perpendicular direction. This may be a benefit, I'll admit it, of finite element analysis. What PT data is going to do, unless you go into the configuration or the general and tell it something different, general setup, it's going to assume you have the minimum required by code in the perpendicular direction, which is 125 PSI. So you can override that and put in what you have, or you can just let the program assume a minimum in the perpendicular direction. So the average pre-stressing compression on this joint, on this critical shear joint happening on 4 sides is 147 KSI. So we take that VP as 0. In the first equation, this stuff gets pretty easy, but remember, you're doing hand calculations, you can be slightly off when you have a 5,000 PSI slab, and you're not sure exactly why you're slightly off. It's because you're not allowed to have more than 4,900 PSI under that radical. So VC is 289 PSI for the first equation. The second equation, that's that gamma S, that 40 right there. Again, you're limited to 4,900 PSI in this radical. Another reason that you might be off slightly in your hand calcs. And that results in 350 PSI. We had to use the lesser of the two. So this is the big winner. And for punching shear stress, we have a phi factor of 0.75. For shear, we have 0.75 phi factor, capacity reduction factor. So let's see how we did. We look at PT data. The maximum allowable shear stress is 217. We nailed that at the interior joint. And we calculated a shear stress. Remember, 290, I think I calculated 289 or 291, sorry. Not bad. Not bad. Okay, so this says we don't work. We don't work. This does not work. This design violates the maximum allowable shear stress for punching shear. We are going to have to use shear studs, stud rails. Now, I'm not doing that in this video, but the next video we will go through and design all of these shear studs. This is very valuable. Knowing how to do this is very valuable. The people who sell these shear stud programs, I don't think they really want you to know. When I wrote my own shear stud program, I had to gather so much information from so many different directions because nobody showed the whole thing all the way through. I had to piece it together using about 3 or 4 different documents, suppliers, ACI 421, Dacon. I think they want to give you about 80% of it, and so that you're left a little confused and just buying their software. But I love those guys. Those guys have all been great, very helpful. They provide shear studs in all the different ones. I don't even want to list all of them because there's many who provide this, but I use my own software that I wrote. So anyway, we pretty significantly violated the shear capacity, the punching shear capacity, and we're going to have to supplement. So that's not at all unusual in post-tensioning. We've got thin slabs. Okay, so I'll see you in the next video.